Hello, I'm Hugh Manfield and welcome to my science channel. And today is another episode of what Einstein got wrong. And since my last video was on about how to correct special relativity, I thought I would do a video on how to correct general relativity. So let's understand what general relativity is. Well, Einstein was dissatisfied with special relativity because it only allowed you to compute the differences between 2-point cases. But he wanted to understand what was going on in an entire gravitational field. So when he began to develop general relativity, he began with extending the equivalence principle to accelerated reference frames. And since he had this space denial philosophy, that became sort of difficult for him. And that's why in my previous video I've shown how some of the foundational thinking of general relativity is just bad. So let's look at the timeline of Albert Einstein's life and see why he thought the way he did and see what happened after he developed general relativity. Now, he published general relativity in 1916 and 17, and it was shortly after the discovery of the atomic nucleus and the development of the Bohr atom. And as time went on, galaxies were discovered. At the time general relativity was published, everyone believed we lived in an island universe and that there were no other galaxies known to exist outside of our own Milky Way. But Edwin Hubble discovered that there were actually, these nebulae were actually distant galaxies just like our own. So that was new. Quantum theory hadn't even been developed in 1916. It was a whole decade later before it would come about with the Copenhagen interpretation and the development of the uncertainty principle. So Einstein didn't know anything about quantum theory when he developed general relativity, and there's no wonder that the two theories are incompatible. Let's see what else happened. Shortly into the 1930s, Fritz Zwicky became puzzled at why galaxy clusters orbited as fast as they did, and he proposed something called dark matter. And once again, Einstein probably thought, well, this sounds very interesting, but let's wait and see if it's really true, if it can be verified. And he would have to wait a long time. Now, one thing I haven't even shown on these charts is we got World War I and World War II taking place in Einstein's homeland, which had to be fairly disruptive to his work and his collaboration between other scientists. And during World War II, fission was discovered, so E equals mc squared was verified. That was a big feather in Einstein's cap. And the first atomic bomb was detonated, and that was something of concern for all of us. But dark matter wasn't even verified until after Einstein's death by Vera Rubin in the 1960s. So general relativity was developed with no idea about dark matter, no idea about quantum physics, quantum theory, and something that's even clear off the chart is dark energy, the accelerated expansion of the universe. There's no way he knew anything about any of that. So it's no wonder that general relativity doesn't take any of that into account. So really, it's time that general relativity should get an update. So, can general relativity be fixed? Not the way Einstein did it. I would suggest you take your GR textbooks, put them up on a high shelf, and put a caution tape across it. Do not use. General relativity is based on classical concepts that predate most of modern physics. We need a new theory of gravity built from scratch that takes these new discoveries into account. And fluid space theory is here to fill the bill. So let's see what does fluid space theory do? Well, it uses relativity to derive gravity, same as GR. Both get a check. It reduces to Newton's law at low energy levels, check and check. It preserves curved space, just as general relativity does, so both are checked there. It predicts gravitational time dilation, it predicts gravitational waves, it predicts the deflection of starlight near the sun, and it correctly predicts the precession of the orbit of Mercury. So fluid space theory does all of the good things that general relativity does, but it comes without that classical baggage. Let's see what else it does. Fluid space theory accounts for dark matter. General relativity does not. Fluid space theory predicts expanding space-time, and so does general relativity. But fluid space theory predicts contracting space-time. And there's probably a solution to GR that's been forgotten about and abandoned that does the same thing, but it was never used and never considered pertinent. Well, in understanding dark matter, contracting space-time is very important. Another thing fluid space theory predicts is it solves the problem of missing antimatter. Fluid space theory predicts that there will be two forms of matter, one with an inflow field and another form with an outflow field. And these will be matter and antimatter. And these will give matter and antimatter different emergent macro behavior. The inflow field will create a contracting space-time surrounding matter. And we see that in the clumping together of matter in the universe, normal matter, and we've attributed that to dark matter. Well, antimatter, on the other hand, will have just the opposite. It will have an expansion field, which will tend to make it disperse. So antimatter is likely not going to be able to form stars, certainly not galaxies, and certainly not large-scale filament structure that we see happening with matter. In fact, the voids between the large-scale filament structure are probably going to be filled with dispersed antihydrogen. And not being able to form stars, antimatter will not be found in any of the higher elements. So that's something that will only be seen with a fluid space analysis and predicted by fluid space theory, not by any other gravitational theory. Fluid space theory works without dark energy. To get GR to work, you've got to load a whole bunch of dark matter and even more dark energy into the model to make everything work. In fact, 95% fudge factor. If you watch my introduction to fluid space theory, you'll see what I think about that. It's a general fail. Another thing going for fluid space theory is that it is easy to visualize. GR is almost impossible to visualize, but to visualize fluid space theory, all you have to think of is fluid flowing down a funnel. Easy to picture in your mind. We've all seen it, and we know how that works. Fluid space theory uses simple math. You don't need any of the tensor calculus or the fancy math that Einstein used to develop general relativity. And another thing going for fluid space theory is that it can be understood by most people. In fact, I would submit that even Einstein didn't understand general relativity when he published it. So what else does fluid space theory do? Well, fluid space theory is compatible with quantum field theory. In fact, fluid space theory leads to the formation of a particle type object that will be complex harmonic oscillator. Fluid space theory has no singularities. There's no need for a place for the mass to go because the mass is the flow field, and the flow field continues down into an infinite corridor where the acceleration of gravity vanishes. Fluid space theory predicts E equals mc squared. Now this may not be completely fair, but general relativity does not predict E equals mc squared. That was predicted by special relativity. Fluid space theory explains the nature of matter. If you watch my earlier video on the heart of fluid space theory, that's where I explain how fluid space theory predicts and lets you visualize the way matter is formed in a spatial flow field. You can understand the true nature of matter. Fluid space theory describes a more complex cosmology. Now, when Einstein developed his cosmology, he was developing it for a static island universe. Well, we know that's not true. And although he extended it based on the new discoveries, it still carried along the baggage of his classical thinking. And it was really oversimplified because, according to his equation, the cosmos is only doing one thing. It's expanding. Fluid space theory says there can be regions of the cosmos that are expanding and other regions that are contracting, and that there may be a continuous dropping of the vacuum energy level, which would lead to an overall cosmological redshift. So there are three, possibly more, things going on in the observed redshift of distant galaxies. Fluid space theory is wide open for development. No one around the world is even thinking about it or working on it at the present time, except for probably me. And fluid space theory puts new tools in the hands of physicists. What do I mean by that? Well, when you consider a flow field, you'll have a velocity vector field and an acceleration vector field. That's a lot more to work with than just the Einstein metric. And having these flow fields, computational fluid dynamics would be a great tool to start studying gravity and possibly even modeling fundamental particles. So a whole new approach, a whole new open area for development and research. In conclusion, Einstein developed his theory of 1916 based on classical concepts, and he didn't account for all of the discoveries which hadn't happened by then. As developed by Einstein in 1916, there's no way he could have anticipated the discoveries that were going to be made in the future. And that's why general relativity doesn't cover dark matter or quantum field theory. GR, as developed, can't be fixed. It's time for a new theory of gravitation built from scratch to include the discoveries of the 20th century. So, his theory of 1916 cannot be brought up to date, and it's time that people start using fluid space theory. And currently, there's only a couple of places where you can learn about fluid space theory. You can learn about it in my book, Einstein and Aliens, which is available on Amazon.com, and you can watch these videos. I've structured my video as Fluid Space Theory 101. If you watch the videos starting from the introduction and the numbered videos in order, they will take you through the development and build the ideas that lead to fluid space theory. So I hope you find this interesting and that you're willing to learn more about fluid space theory. Until next time, I'm Hugh Manfield.